Hello. Yeah, I wanted to look at the last two examples from the worksheet from Monday's class. So here we're given that our coffee consumption is increasing at 0.7 cups of coffee per day, and that the cost for coffee rises at a rate of 50 cents per cup. So part A, we're currently spending $12.50 on coffee each day. How many more cups of coffee will be consumed in 12 days than are being consumed today? So here we know that our consumption is increasing at 0.7 cups per day. And if we multiply that by 12 days, we'll end up with 8.4 cups as the total increase in the number of cups of coffee that we will be consuming 12 days from now. For part B, we're asked how much more money will we be spending in 12 days than we're spending today. So if we're going to be drinking 8.4 more cups of coffee in 12 days than we are now, and we know that our costs rise at 50 cents per cup, then our total cost then would be increasing by 50 cents per cup multiplied by 8.4 cups. And if you compute that product, you end up with $4.20 as the increase in our costs. For the third part, we're asked the rate at which our coffee costs are increasing in dollars per day. And there are two ways to answer this. One way to answer this would be to take the number we just built, $4.20, and divide it by 12. And if you divide $4.20 by 12, you'll end up getting $0.35 or 35 cents per day. The other way to get this answer for the rate at which our coffee costs are increasing in dollars per day would be to compute it directly. We know that our consumption of coffee is increasing at 0.7 cups per day, and we know that our costs increase at a rate of $0.5 per cup. And if we take the product of those two, you end up with $0.35 per day. So the increase in cups per day multiplied by the cost in dollars per cup gives you the increase in dollars per day of 35 cents. And of course, part of the point of this problem is to motivate the way the chain rule works, where we compute the derivative of a composite function by multiplying the two corresponding derivatives of the outside function and the inside function. The last problem gives possible functions for M of C, the amount of money spent when we consume C cups of coffee each day, and function C of T for the number of cups of coffee being drunk each day. And I would just point out that the number of cups of coffee really is increasing at 0.7 cups per day because the derivative of C is 0.7. And our current coffee consumption, according to this formula, when T equals 0, is 50 cups of coffee per day. When C equals 50, we could compute M of 50 and verify that that really is $12.50, as in problem 15. Even better, if we take the derivative of M, we could verify that the derivative is 0.01 times C, and when C is equal to 50, the derivative of M would be equal to 0.01 times 50, which is 50 cents. So our costs currently would be increasing at 50 cents per day. So here are a pair of functions that match the description from question 15, which is kind of cool. That isn't what the question was necessarily asking us to do, but it's interesting in any event. What we're actually asked to do is to write the function m in terms of the variable t, and then use that expression to compute the derivative of m at 0, and then to compare our answer to what we had found in problem 15. So if you do the substitution, m as a function of t is 0.005 times the function c squared, and here I've replaced c with what it is in terms of t. If I wanted to go and take the derivative without using the chain rule, I would need to multiply this out. So first square the binomial and then multiply by 0.05. So if I square 0.07t plus 50, I end up with 0.49t squared plus 70t plus 2500. And now I have a constant multiplied by a polynomial. I can take the derivative m prime of t. It's equal to that constant, 0.005, times the derivative of the polynomial. So I'm going to have 2 times 0.49, so that's 0.98 times t to the first power, plus the derivative of 70t, which is just 70, plus the derivative of 2500, but that's 0 because 2500 is a constant, so I can ignore that. So now to compute the derivative when t equals 0, m prime of 0 will be equal to 0.005 times 0 plus 70, and 0.005 times 70 is 0.35. And the units here for the derivative of m, it's units of m, which were dollars, divided by units of the variable t, units of time. This is measured in dollars per day. And so it's interesting that this exactly corresponds to the answer we found previously for the value of the derivative of this function at time t equal to 0. Now, as you'll read about in the section for finding derivatives using the chain rule, an alternate path for computing the derivative of this function would be as follows. If we think of m of t as being a constant times something squared, our inside function might be 0.07t plus 50, and our outside function then would be 0.005 times some variable squared. The chain rule then would tell us that the derivative would be the derivative of the outside function. So taking the derivative of a number times something squared, I'm going to have 2 times that number, so 0.01, 2 times 0.005, times that quantity 0.7t plus 50 raised to the first power. So here's the derivative of the outside function, and then I would multiply that by the derivative of the inside function. And here the inside function is linear, and so its derivative is just the slope, its derivative is the slope, 0.7. Now, indeed, it turns out if we were to multiply these different components together, we would end up with exactly the same derivative we had found above. And if we set t equal to 0, we would find that m prime at 0 is equal to 35 cents per day, as we had done before. Anyway, so that's our the last 2 problems from the worksheet, and should have us in a good place for reading the section about the chain rule. Take care, and we'll see you in class.